Hey, it's Dr. J. Today we're going to talk about some more applications of the chain rule. To get the lecture started today, I've got an example very similar to some of the business applications that we've seen in the past. However, the complexity of the functions is now increased due to the fact that we have this new rule. Sort of gives us the ability to go after more complicated functions, in particular functions like this, where you would apply the chain rule, because you can see that this is a chain of different types of functions sort of composed together. This is a composition of a linear function, 4x plus 2, and a square root function. So, we've already discussed what marginal cost is. Remember, marginal cost is the derivative of cost. And we want to produce 16 artificial brains in a laboratory as given by this function. So first we find the derivative of the cost function. Now that we have the chain rule, we should be able to do that pretty easily. The derivative of 850 is 0. 270 is a constant, so it comes out. It's probably a good idea to rewrite this as 4x plus 2 to the 1/2. Been doing that a lot when we see a square root. And then when we use the power rule, that'll be 1/2 times 4x plus 2 to the negative 1/2. And then the chain rule, the derivative of 4x plus 2 would be 4. This is all multiplication. So it's 270 times 1/2 times 4x plus 2 to the negative 1/2 times 4. So our marginal cost function is going to be 270 times 1/2. That'll be 135. And then times 4. I'm just going to bring the 4 to the front. Over the square root of 4x plus 2. So that'll be 530 over the square root of 4x plus 2. I do have my calculator, my phone handy today, so I'm just going to double check. 270 times 1/2, which is really just dividing by 2. That's 135, and then times 4. I'd rather check now. Oh, I'm so glad I checked. I was trying to be tough and not use my calculator, and that would have been a problem. 540. It's always better to measure twice and cut once, as old Mr. Jordan, my father, used to say. Okay, so now we're going to plug in the 16. So we have 540 times the square root of 4 times 16 plus 2. That's going to be 66. Square root of 66. Let's make sure that's right. 16 times 4. I think I'm right this time. Plus 2. Yeah, I'm right this time. And then you've got the square root. Square root, it's about 8.12. So we'll do 540 divided by 8.12. And that'll be $66.47. Because I'm rounding that 9 here. Oh, I hit the button. But there was a 9 that rounded the 6 up to a 7. So this is the marginal cost. The marginal cost is $66.47 per brain. I should tell you what this means. It's not the same as the average cost. It's not the average. It's the cost to produce the next brain. Or to manufacture the next brain. So the next brain would be the 17th brain. So essentially, you've already made 16 brains, right? That's what marginal cost is. It's like saying, okay, we've already made 16 of them. What's the margin on the next brain? So the 17th brain would be 66.47. All right, that's that little increase. I'm not doing average today. Maybe I'll do it. We'll do marginal average maybe, but I mean, if you're curious, you made 16 brains already. The average is like, I don't know, $190 or something. You could figure that out. I'm not asking it today, but if you're curious, what you would do is you wouldn't take a derivative, right? So for average, you would just plug in 16 into the original function and then divide by 16 after you've figured out the cost of the brains, and that will give you the average. Okay, so this is a margin. It's just the cost to produce the next brain. Now we are going to do marginal average. So I better keep this. I guess I don't need to keep that. Let's do find the marginal average. Cost to produce or to make 16 brains. So that's where we take the cost function, we divide it by x. So again, I said if you're curious about just what the regular average is, or simply average, you could stop right here and just plug in 16. All right, I am actually curious, so I did it before the video. It's about $190 a brain. Not too expensive to make an artificial brain. Now, to get the marginal average, now we have to take the derivative of this thing. And I'm going to need more space. So now we have a combination of the chain rule and the quotient rule. So we have the chain rule, which is right here inside the chain, and then we have the quotient rule. So let's do the quotient rule first, because that's the sort of the overarching operation. It's a quotient first. The chain occurs inside of the quotient. So we're going to have the denominator squared. We're going to have the derivative of the numerator. Shoot, I should have kept that. What was it? It was 540 over the square root of 4x plus 2. I just remembered that. That's the derivative of the numerator. That was a C prime. So I save me. Good thing I remembered it, because I did erase it, but I have a relatively good short-term memory. Not as good as it was when I was your age, but okay. So that's the derivative of the numerator times the denominator minus the derivative of the denominator, which is 1, times the numerator. 850 plus 270 square root 4x plus 2. Now, had I not saved the result of step 1, then in the quotient rule, I would have had a lot more work right here. That would have been a big mess. So saving your result of the first part is very helpful. I'm going to save this answer, 66.47. That's MC, marginal cost. All right. So we got marginal average cost. It's going to be messy, but that's okay. We can handle it. It's going to be 540x over the square root of 4x plus 2 minus 850 minus 270 square root of 4x plus 2 over x squared. I'm not going to try to simplify this too much. I'm just going to go ahead and plug in 16. You can spend 15 minutes trying to simplify this, and it's going to not change the answer one bit. So let's just plug everything all in. 540. Oh, by the way, we already know this. 6647. Yeah, we already have that. I could do it again if I want. If I made a mistake. Oh, actually, no. We know this is 6647. Glad I didn't screw that up. This one has an extra x. So it's going to be... Was it 6647? God, my short term. I'm just bragging about my short term memory. Let's see. Square root of 66. And then divided by 540 divided by that. Yeah. $66.47. And then times 16, because this one has an extra x. So this is going to be $1,063.51. So I'm plugging in 16 everywhere there's an x. And then I'm going to simplify all this. So I've got marginal average cost. Let's start here. Square root of 66 times 270. All right, and that's negative. That's negative 2,193. And I'm just going to work backwards here. Minus 850. And then plus 1,063.51. And then divided by 16 squared. Negative 7.73. What is 16 squared? I should memorize that. When I was a kid, it was 256, but I always forget. I'm going to do a safety check right here. So I wrote everything down. I've got 1979.9803. I just wrote dot, 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 dot. I don't need the rest of those decimals. Divided by 256. And it's negative. So just to double check that my marginal average cost, also known as the MAC, in business terms, marginal average cost, which is actually pretty cool. Yeah. It means that each time I make a new brain, the next brain is costing me $7.73 less than the last brain that I made. Which, if you think about it, it's like, okay, this was your marginal cost, right? MC 66. So that was positive, right? So let's just kind of put all this in context before I erase it, because I think this is super important to understand what your answers mean. I might ask you to interpret these results. Right? Sometimes I do, sometimes I don't. Sometimes I just ask for the number, and sometimes I say, interpret what this means, right? So it means that the cost to produce the 17th brain is $66.47. Yeah, that's what this answer means, the MC. The MAC, the marginal average cost, says the next brain is going to cost $7.73 less than the brain that I just made. Right? So you can think about that. That means the brain before this brain costs $7.73 more because it's gone down. Right? And then it's going to keep going down and keep going down by a different margin. The margin doesn't stay constant. That's the reason why we have to use calculus. If the margin stayed constant, then every graph would just be a line, right? And everything would be going by the same amount. It'd either be going down or it'd be going up by the same amount every time. That wouldn't be calculus. That would just be algebra. But in calculus, every increment, it's changing a little bit. So when we're on the 16th, this tells you how much less the next brain's going to cost. You can think about it like taking a series of snapshots, right? So when we get to the next brain, right? I'm not going to. I'm done with this problem. We got the two answers we wanted. But if I wanted to go, let's go to the 17th brain. Then I could do the whole problem again, and that would tell me the cost of the 18th brain, and it would tell me how much cheaper the 18th brain is going to be. It's going to be probably, I don't know, maybe $6.50 or something. I have to do all the math, and I'm not going to because we got a lot of problems to do today. So stop, think about your answer, double check your results on your calculator. Never trust your first mental, math or instinct or intuition. Sometimes it's right, sometimes it's wrong. So now we have a company that sells ice machines in the desert. So you ever seen these popping up, right? It's like there's a machine, there's no people, you just put the dollar in or you put the quarters in and a big bag of ice pops out of it. It's great. You don't have to go inside the store. Some of these machines also sell water too. They're great. I love them when they're so convenient. They put it right there in my neighborhood where when I'm leaving town, I need some ice. I can just pull up and throw a dollar in there and out pops a bag of ice. All right. If they sell X machines per year, the price of each machine is given by PX is $3,800 times e to the negative 0.34x. So this is the price demand function. It's telling me the price of each machine. Okay. And it's based, of course, on how many I sell. If I only sell one machine per year, then plug in one, and that tells you how much that one machine would be priced at. It'd probably be pretty expensive. But as you sell more machines every year, the price can go down and you can lower the price. One thing I do in my algebra courses is I don't do calculus. I just have students make a chart, like, basic algebra, and plug in various numbers for x and sort of look for a pattern or look for a relationship. In this class, I could do that if this were the opening act of business calculus, but we're halfway through the semester by now. So I'll just say, in your mind, you can imagine that chart. I'll leave that to you if you'd like it as an additional exercise. All right. So find p prime of 10 and interpret the results. So find p prime of 10 and r prime of 10. This is a lowercase p. You got to be really careful with the p's. I wish there was another letter for price. I have seen other professors use different letters. I've just always used p and just had to be careful with what I do. All right, so p prime of 10. Well, first I need to know p prime. So let's just do a little scratch work here. P prime of x, the derivative of 3,800 times a function is just going to be 3,800 times the derivative of that function. Remember, e is one of those special functions where the derivative is just equal to itself, but then because of the chain rule, you got to take the derivative of the power. So that's like 3,800 e to the g. It's reminding you about and then this is g prime of x. So g of x is the power. F of x is the e part. And then p of x is p prime of x is the derivative. All right, so that's going to be, I'm going to combine the 34 and the 3,800. So I've got 0.34 times 3,800. That's negative 1292 e to the negative 0.34x. So p prime of 10 is negative 1292 I'm just going to give myself some more room here. Sometimes it's nice to put a little tail on your p so that you know it's price and not profit. I should use r for price. It's too late now. I've already used p, but price, I can use r. I think we like to use R in mathematics for rate, but I mean, a price is a rate. I'm just thinking out loud here. So that's going to be negative 1292 times e to the negative 3.4 power. So do the power first. You've got your E button on your calculator, so e to the x. Yeah, that'll be that number. And then times 1292. Negative 1292. So that's going to be negative 43.12. Yeah, it's 0.118. I'm ignoring the rest of the decimals. The 8 rounds that up to 12 cents. All right, so that is the marginal price. Yeah, the margin of price, which essentially means that the price of the 11th, right? It's always the next one. The 11th ice machine is going to be $43 less, right? The price is decreasing by $43. So the next ice machine costs $43 less than the one we just made. maybe I shouldn't use the word cost. That's what it costs if you're a buyer, if you're buying ice machines. This problem is about revenue. So we're looking at it from the other side. It's how much we're making when we sell the next ice machine. All right, so revenue. Remember, revenue is just price times X. Yeah. Now we're selling them. So this is just talking about the price of the machines. Now we're actually going to sell them. So we're going to multiply 3,800 e to the negative 0.34x times an additional x. Typically, we just put the x with the 3,800. You could leave it off on the side like that if you choose. I don't choose to do that. I like to put this x in front of the e with the 3,800. Okay. So that's our revenue function. I want the revenue from selling 10 machines. So I want the marginal revenue. So the derivative. Now we have a product rule. Yeah. And again, I could have left it like this with the product rule here. But I've just always been trained to put the x in the front and then make that the product. It doesn't matter. You're going to get the same result anyway. So the derivative of the first factor is 3,800. 3,800x, so the derivative is 3,800, times the second factor, plus the first factor times the derivative of the second factor. But we already know the derivative of the second factor. It's e to the negative 0.34 x times negative 0.34. So it's 3,800 e to the negative 0.34 x minus, you see how this negative is going to change this positive to a negative. And it was 1292, right? Because I've already done that, multiplying 0.34 times 3,800. It's the same 1292 we had earlier. X e to the negative 0.34x. And so we want R prime of 10. So what's the marginal revenue from selling 10 ice machines? All right. So it's going to be 3,800 e to the negative 3.4 minus 1292 e to the negative 3.4. Oh, shoot, we have an extra x here. So that's 1292 times 10. I'm just going to add an extra 0 here. And then 0.34 times 10 is going to be 3.4. So remember, x is 10. X is 10. So that just adds a 0 here. All right, let's see. 3.4 negative e. So that's the e to the 3.4. How are we making negative revenue? Revenue should not be negative. Oh, no, it can be. Never mind. It's fine. Don't listen to me. I was just pausing for a second. This is marginal revenue. Marginal revenue. Marginal revenue can be negative. It's just slope. All right. Now, just before I finish this problem here, I was looking at my calculator and about to panic, but revenue can never be negative. Just before you take the derivative, this is always positive because revenue is always in quadrant 1 if we were to draw the graph. Revenue essentially goes like this. It's a curve. Right? It's always positive. Right? It's changing based on X. It's not constant, but it's never going to be negative. So if I would have got a negative revenue up here, I mean, you do see a negative sign, but it doesn't mean it's actually a negative number. Then that would have been a problem. This is marginal revenue. So we're going to interpret the results in a second. So where was I? I'm going to show you a trick to make this a little easier. 3,800 minus 12,920. You could factor out the E. As long as they're the same power, you can factor it out. And then now I've got 3,800 minus 12,920, negative 9,120, e to the negative 3.4. I'm saving this to talk about in a minute. I don't know if this makes it any easier, but it does for me because I'm using a cell phone calculator. I'm only going to have to plug this into my calculator once. So 3.4 negative. So do the power first, then do the E. So that's E to that power, and then times 9120, which is negative $304.36. And the 4 is not big enough to round that up to 37. So let's interpret this result now. When 10 freezers, or ice machines, I guess. An ice machine is just a freezer. Are demanded. That's what we call that. It's the demand, right? I guess you could say they've been sold too, but why were they sold? They were sold because they were demanded, right? So in other words, you can think of it like somebody called and said, hey, I need 10 ice machines. I demand 10 ice machines. So they're demanding, or the customers are demanding 10 ice machines. They're not all necessarily being sold to the same person. So when 10 ice machines are demanded each year, the price, that's this one, is decreasing by $43.12, or you just say 43.12, $43.12 per machine. And the revenue is decreasing. It's also decreasing by, or at a rate of $304.36, again, per ice machine, or per ice machine, per freezer. So again, this is decreasing revenue and decreasing price. Which, I mean, that should make intuitive sense, right? If the price that you're selling them for is decreasing over time, well, then the amount of money you're bringing in is going to decrease as well. So now we need to combine the last two examples together and think about making a profit, right? Because you can lose revenue, but still make money, which is interesting, right? Because remember, this is all decreasing, but it's still in quadrant one, right? If you think about the graph, yeah, you're in quadrant one and you're heading down, but you're still making money. You're still, as long as you're above the x-axis, you're actually still making some money. If you are making more revenue than cost, then you have an actual profit. So example 3, suppose the revenue is given by this function. So I'm just giving you the revenue function. And the cost is given by this function. Find the marginal profit and the marginal average profit, remember MAP, when 200 units are produced and sold. And I'm skipping the story time on this one. I don't know. Are these artificial brains? Are these freezers? We could just call them units. Yeah, just general widgets, gadgets, gizmos, whatever they happen to be. Okay. Sort of abstract X that we're selling. All right, so we want marginal profit and marginal average profit. So MP and MAP. So first we got to find profit. Now these are the easiest type. You just have to make sure you get it in the right order. You take the revenue first, and then you subtract the profit. Normally I use an extra set of parentheses, but we've gotten good at this, or we've seen this several times, so I'm just distributing now and I don't have to worry about wasting another line. So first let's do marginal profit. That's the easier one. It's just taking a derivative, term by term by term. So we're going to bring the 2 down. It's going to be negative 0.46x. This one has an invisible 1, so the 1 times 450, and then the x disappears. Technically, it becomes x to the 0. Yeah. If you like to see the pattern here, that's what happens. This becomes 0. Derivative of 710 is just 0. And then this is that really easy derivative. ln is 1 over 8x plus 1. But then don't forget the chain rule, right? Times 8. And make sure the times 8 is up in the numerator. Sometimes it's better to write it up top like this. Okay. So this is negative 0.46 times x plus 450 minus 8 over 8x plus 1. And we're going to sell 200 units. And I'm doing a little bit of mental math. 8 times 200 is 1600, plus 1 is 1601. Just to save my board space because I'm really getting low on space here. So what do we got? We got 0.46 negative times 200. It's negative $92. Plus $450. All right. So that's going to be $358 minus this. This is almost zero, but I just want to make sure it's not a penny. If it's even a penny, I have to include it. Nope. It's not even a penny. So it's 357.995, which is still 358. So marginal profit is at 10 units is $358. I would accept 357.99. There is a tolerance, but really this is less than a penny, so I don't know. If you do this and you round it up to 1 penny, it's so close to half a penny. I have a tolerance. My tolerance is about half a penny. All right, so I would just keep it at $358 because this is essentially zero. All right. That's actually pretty cool. That I don't know what these are, but whatever they are, if you sell 11, this is how much you're going to make on the 11th gizmo, whatever it is. Right? You've already made your money on the first 10, right? This is a margin. So this is how much more you're going to make by selling one more of these things. So now we got to do the map, the marginal average profit. First, we need the average. And this is a little bit more work. I got to copy this whole thing down again. 0.23x squared plus 450x minus 710 minus ln 8x plus 1. All right, and so now I want, oh, shoot. That's not the average yet. I got to divide it by x. Okay, now it's the average. It's got the hat or the bar, so that's the average. Again, if you want to know just the average, you could just plug in x now. Right? There are some questions where I ask for just the average. If I don't use the word marginal, then you just don't do the derivative. You just plug in the x. That tells you on average how much profit you're making for each gizmo or whatever it is you're selling. I've already done those examples where you don't take a derivative. So today, I've already gone on for 45 minutes. I got a lot to cover today. I don't know how we're going to get through it. But we're gonna, right? So buckle up. I think I've shown you this trick before where you divide them individually. Yeah. And then this becomes 0.23x plus 450 minus 710 over x minus ln 8x plus 1 over x. So then when you take the derivative, it's a little bit easier. The derivative of the first term, it's just going to be the constant, 0.23. Right? The x drops off. The derivative of the second term is 0. Yeah. The derivative of the next term is 710 over x squared. Remember, that's a reciprocal. And now this one's a little tricky. All right, this one's a tricky one. This is a quotient rule. Quotient rule. So I'm going to use some extra brackets here. Denominator squared. All right, so the derivative of the top, 1 over 8x plus 1 1 over 8x plus 1 times 8. Just going to put the times 8 on top. Times the bottom, x. Minus the derivative of the bottom, 1 times the top, ln 8x plus 1, all over the bottom squared. Now don't get too concerned. This is going to clean up. I don't really want to say nicely, but it's not that bad. This is going to be 8x over 8x plus 1 minus, times 1 over x squared. Yeah. Plus, you have a minus, ln 8x plus 1 over x squared. And so I can cancel x and x squared. Don't try to cancel the 8s. They don't cancel. If that plus 1 wasn't there, then you could cancel the 8s as well. But that plus 1 screws that all up. And then you have 8x plus 1 times x. So that's going to be like that. Plus ln 8x plus 1 over x squared. So that is your marginal average profit function. I will mention, if this is, making you squirrely or giving you anxiety, you could have stopped earlier, right? You got to get through this stuff, but you can plug in the x as soon as you've done the derivative. I was just trying to give myself a little less work to do. So I've got p hat prime of 10 is negative 0.23 plus (710) over 10 squared, which is going to be 100. Now you know why I picked 10. Minus 8 over 810. Look at how I did that in my head. 8 times 10 is 80. Plus 1 is 81. Times 10 is 810. So it gets better when you plug everything in. ln of 81 over 100. All right, 10 squared. So it looks much more complicated than it is when you actually plug in the numbers. And a nice thing about this is all the decimals are going to be very nice. That's going to be 7.1. 8 divided by 810. That's tiny. That's barely a penny, but it is close enough to a penny. Close enough to 1 cent that I should probably keep it. How about this one? 81 ln natural log of 81 and then divided by 100. That's 4 pennies. All right. So that's about 4 cents. That's about 1 cent. And then I'm just going to work backwards. So that's about 4 cents. Let's subtract 0.0098765 Oh, that's cool. 98765 That's pretty cool. 8 divided by 810. Fun fact. All right, and then plus $7.10. And then minus 23 cents. And that gives us positive $6.90. So those are our two answers. So my marginal profit is $358. That's how much I would make selling the next gizmo, right? And then the average marginal profit or marginal average profit, it means that on average, I'm making an additional $6.90 on each additional unit, right? At least so far, right? When you're at 10. When you get to 11, then this number will change. And then when you get to 12, that number will change. And it changes. And what we're going to do in chapter 3, just kind of a little preview, is we're going to keep our eye out on when that starts to turn. And then we want to pull the plug. Yeah, because we don't want our profit to turn around and go negative. Right? We want to always stay up if possible. I mean, unless we're trying to rip somebody off. Which we're not. Oh, I got something new today, right? What a day to pick it when I'm got all these examples to do, but I got something new today. I don't know what you've seen in your math life, but suppose you you sell an item and the number of units depends on the price. The number of units demanded depends on the price, which it kind of already did, but the way we said it in the last example, before that, was that the price depended on the number of units. But what if we do it the other way around? The number of units depends on the price. And again, this is a lowercase p. We have not seen this yet. We weren't ready for it because it required some rules that we didn't have yet. But now we've got the rules, we can handle this now. So in other words, this is reversing the price demand function and saying, well, if you plug in a price, this will tell you how many people will buy the item, right? So an example, if the price is $10, then the number of units would be whatever that comes out to be. I should be able to do that in my head. 1560 divided by 5, 312. So this is my demand. This is my price. So if I'm charging $10, I plug in 10 for the price. 0.3 times 10 just comes out to be 3. That's why I picked 10. 3 plus 2 is then 5. Divide this out. 1560 divided by 5 means 312 people or 312 of these items will get sold if they're $10 a piece. Again, if this was not calculus, I would probably make you have a chart where you went, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you'll see that as the price goes up, the demand goes down. If you only had one item, you would sell more of them. I mean, if the price was only $1, you would sell more than 312. If the price was $20, you would sell less, right? So as the price goes up, the demand goes down. I don't know why I keep saying that. I'm sitting here staring at the camera going, how many more times could I make that obvious? So maybe because it's new and I just want to make sure I hit the nail on the head. So let's find what's called X prime of P. It's called the marginal demand. Now, marginal demand must be a whole number because you can't sell half of an item, right? So we're going to round this to the nearest whole number. So this is going to be the derivative of the top, which is 0, times the bottom, minus the derivative of the bottom, 0.3, times the top. I guess we could have done this before. Divided by the denominator squared. I just needed the quotient rule. Maybe I was thinking the chain rule might be appropriate for this. So it ended up in this lecture, but I didn't actually end up using the chain rule. So this kind of just snuck in here. So this is X prime of P. Now this is 0. This is going to, well, I guess that's kind of like the chain rule, right? It's the derivative times the derivative of the inside, which is 0.3. So 0.3 times 1560. So that's negative 468 over the denominator squared. So what does this tell us? This tells us how the demand is changing with respect to price. So what is X prime of 20? Well, let's see. 468 over 0.3 times 20 plus 2 squared. 468 over 6 plus 2 squared. Negative 468 over 64. I'm just doing some mental math here. So that's negative 7.31. I'm just keeping it $7.31. So what does this mean? This means when an item is priced at $20, the demand is decreasing, and I got to fix my answer here. As soon as I wrote the word demand, right, round to the nearest unit. So you can't have 0.31. I know I said that like 3 times, but my brain switched back to dollars and cents mode. But I realized the price of the item is $20, right? there's the dollars and cents. The demand is decreasing by 7 units per dollar. Units per dollar. So in other words, every dollar that I raise the price, 7 less of these items will be sold. The demand will go down. Yeah. But you can also flip the script and go the other way. If you lower the price by $1, then 7 more units will get sold. So remember, demand and price are interrelated. If one goes up, the other goes down, and vice versa. If one goes down, the other goes up. So you can read it both ways. Yeah, it's kind of like this. All right. So this represents the slope of a line like this. Right. When the price point, that's one of the reasons why we call that a price point, the dot, is $20, the demand is decreasing by $7 units for every dollar. Okay. Maybe in the next chapter we'll draw some more elaborate graphs. The last example is going to be reviewing something that we did at the beginning of the semester, which is compound interest. Compound interest, AT is P 1 plus R over N to the NT. That's the formula for compound interest. So P dollars is invested at R% annual interest I got to be careful here. So we say R%, but then this is R as a decimal. So I'm just going to be very careful there. Compounded N times per year. Yeah, we call that the frequency. The compounding frequency, N times per year. For T years. So, find the rate that an investment, so this is for those who have the money to invest, so in a secure high yield account, if, an investment of, how much am I going to invest today? $6,000. When the interest rate is 4% over a period, I would say in the 7th year. All right, so if I was to invest $6,000, that's my principal. It's my P. We're using P again. Not profit, not price, but principal. The Percentage, you got to be careful. It's a decimal, so my R is 0.04. And then my T is 7. And I want to find the rate. So I want to find the derivative of this function. Oh, I forgot to say compounded monthly. I didn't read the whole thing. So N is 12. 12 times a year, so every month. So my investment is $6,000. My interest rate is 4%. It's like what we did at the very beginning of the semester. I was introducing calculus to you. N is 12 and 7 years. So first we're going to leave it as T. Don't plug in the T yet. All right, you got to wait on that. Because what we're doing is we're finding the derivative and then we're going to plug in the T. If you plug in the T now, the whole thing will become a number and then you won't be able to take the derivative, right? Or you could take the derivative, but you all know the derivative of a number is just going to be 0. So divide out the interest rate. Oh, that sucks when that happens. And then add 1. You're going to have this giant decimal on here. Just copy down as many 3s as you possibly can. I wish I would have picked a different percentage. But I'm already almost done with my video today, so I'm not gonna change the answer now. I'm not gonna change the input values now. So whenever you get a repeating decimal like that, don't round it. It'll end up causing, you could lose hundreds of dollars by rounding. You can round it at the very end when we're done with the problem, but if you round it now, you're going to lose a bunch of money, right? Especially the larger your investment is. If you were investing millions of dollars, then you would definitely want a lot of extra decimals here. So let's find the rate of change. How fast is my investment growing? A stands for the amount. Or some people call it the amortization of the investment. Or a loan, by the way. This same formula works for a loan. Although when it's a loan, this is not positive money. This is negative money. Now, the way you do it with a loan is you calculate it as a positive number, and then you just say in your head, that's a negative balance. You don't actually put negative numbers into the formula. It screws up the whole formula. Although I guess you could, but I don't. I think of loans and investments as exactly the same thing. All right, so let's take the derivative of this. It's going to be what? It's going to be 6,000. I'm going to pull that out to the front. Then I'm going to take the derivative of this. Now this is going to suck, because it's an exponential function. So the derivative of this is 1.00333333333333. If you want to save space, you can put 3 with a bar. That reminds you that when you type it into your calculator, go 333333333. That's a repeating decimal. All right. The bar has lots of different meanings in math. You can also just go ... That's another way to do it. It means the same thing. Okay, I'm just trying to save space. Times the ln of 1.0033333333 times 12. The derivative of the power, which is 12. Fortunately, you don't have any product or quotient rules here. All right. And now plug in your 7 years. 7 years would be 84. Yeah. 12 times 7 is 84. ln of 1.0033333333. And let me show you a trick. This 12 can come out here, and we'll just change this to 72,000. Yeah. 12 can just come out constant, comes out in front here. All right, let's start here. Actually, it's not a bad idea just to keep that whole thing on your calculator. And then you got your ln. There's your ln. Now I'm gonna write that down in case I screw this up. 0033277900 blah blah blah. And now I'm gonna do this to the 84th power, so times 1.0033333333 to the 84th power. And I got an error, so I have to start over. So I got 1.03333333. Oh, not enough zeros. 1.0033333333 to the 84th power. And then I'm glad I wrote that down. Times 0.003327779. That's enough. Oh, actually didn't screw it up. And then times 72,000. Not bad. $316.88. I just thought I would squeeze that in there to sort of remember where we came from, I guess. Yeah, the business math. Business is not just about, cost, revenue, and profit. That's one side of business. But another side is investing. Yeah, that's sort of the passive way to make money. You just put the money in an investment and you check it from time to time. And so basically this is dollars per year. It is positive, so good, that's good. That means that your investment is growing or increasing at a rate of $316.88 per year. Yeah. Which is interesting because it said it was 4%, right? $4 is only $240 of the original amount, $6,000. So when you see a percentage, it's not what's called a simple interest percentage. You can't just multiply 4% times 6,000 and then do that times 7 years and get the right number, right? Because what's happening, we call that the snowball effect. Yeah. It's compounding, it's growing and growing and growing. And so even though 4% is really only $240 per year, it's because it's compounding over the course of 7 years, and it's been compounded monthly. That's where the 12 comes in. And so you are actually growing more than 4%. It's $316.88, which you could say that's the effective rate. Right? The effective rate is much higher than 4%. It's not much higher, but it's a little bit higher than 4%. All right, I am all out of time. We do have another lesson on the chain rule. I'm going to think about how to present that and how many examples I'm going to be able to get done. Definitely not 10. Today we were only able to do 5, so these word problems take a little while, but be patient, hang in there, keep working forward. We're almost done with this chapter. And so until we see each other again, I'm Dr. Jordan, and I'll see you on the internet.